nearby TRAPPIST-1 star about 40 light years away. What's more, as you can see in this illustration, is that 3 of these planets, marked in green, are in the habitable zone, where liquid water can pool on the surface. In fact, with the right atmospheric conditions, there could be water on any of these planets. So for the first time, we found as many terrestrial planets around a single star, and that's the first time we have been able to measure, in addition to that, both the masses and the radii of these habitable zone type Earth-sized planets. These planets are among the best of all the planets we know to follow up, to see, for example, with the James Webb Space Telescope that we're going to launch last year, the atmospheres, and also to look at biosignatures if there are any. The discovery gives us a hint. 3, take 5, take 7, and you can just imagine how many worlds are out there that have a shot to becoming a habitable ecosystem that we could explore. And what we really have in this story is a major step forward towards answering one of these very questions that are at the heart of so many of our philosophy towards answering that question.
Around the same star, not 1, not 2, but 7 ball. Well, in our case, the basketball would be the Sun, and the golf ball, it would be TRAPPIST-1. So TRAPPIST-1 is much cooler, much smaller than our Sun, and so the planets in its habitable zone are much closer to it, very close to it, with very short orbital periods. And in this graphics, what you can see are the planets which were found around TRAPPIST-1, with the 3 of them which are in the habitable zone, so also called the Goldilocks zones, where liquid water could exist, is the most likely to exist at the surface of a rocky planet. Having 3 of these Earth-sized planets in this habitable zone is very promising for the search for life beyond our solar system. And furthermore, we have, thanks to Spitzer 2, preliminary measurements of the masses for 6 of them. And for 1 of them, our measurement is precise enough to strongly suggest a water-rich composition, which is very exciting because this is one of the planets in the habitable zone. Furthermore, these planets are orbiting so close to the star that they must be, or they are probably, tidally locked, which means they always face the star with the same side, like the Moon, to the Earth. And so if you look at this animation, you can see a view of tidally locked planet with a permanent day side and a permanent night side. The TRAPPIST-1 planet could be just like this. Now, what is also exciting here about this system is that the planets are so close to each other. If you were on the surface of one of these planets, you would have a wonderful view on the other planets. You wouldn't see them like we see Venus or Mars, like dots of light. But as you can see in the next illustration, you would see them really as we see the Moon. You would see worlds with, which would be as large as the Moon and even larger for some of them. So it would be a wonderful view on these planets.
In 2016, and immediately after that, we started doing intensive follow-up with a lot of ground-based telescopes and more than 20 days of continuous observations with Spitzer. And what we're able to find is that we confirmed 2 of the planets that were found in the initial discovery, and then found 5 more planets for a total. Spitzer was launched in 2003, and it was never intended to study exoplanets. So we had to do some clever re-engineering why it's in space still, and it's more than an astronomical unit away from the Earth, so you can't fly out and do anything about it. But we did clever pass in front of the star. We see the amount of light that the star is dimmed by when that planet is blocking it. So the dips you see in this animation are the planets going in front of the star, blocking a little bit of the light. The size of the dip tells you the size of the planet, so we can get the size of the planet directly from measuring the dip. Now, when you see the different planets, they keep orbiting around, and every time they transit, you can measure the spacing between the transits, and that tells you about the orbit, the period of the orbit, how long that year is, and for that planet. And then when we know how long it takes for the planet to go around the star, we also know the distance it is from the star, and that also tells us whether or not it's in the habitable zone. Now, the TRAPPIST-1 system and its planets are in an interesting configuration. The planets are all very close together, and their orbits are spaced such that they gravitationally interact with each other. They tug and pull each other as they go flying around. They orbit.
The innermost planet in the habitable zone is TRAPPIST-1e. So in this illustration, you'll see an artist's rendition of TRAPPIST-1e, which is a really interesting planet for a number of reasons. It's very close in size to Earth, as you can see here. It also receives about the same amount of light as Earth does in our own solar system. This means that in TRAPPIST-1e, you could have temperatures that are very, very similar to the ones that we have here on Earth. The next planet out is TRAPPIST. Now, TRAPPIST-1f has about a 9-day orbit, and during that time it receives about the same amount of sunlight as Mars does in our own solar system. And the final planet, a larger radius than that of Earth, as you can see in this comparison here. And it receives about the same amount of starlight as somewhere in between Mars and the asteroid belt in our own solar system.
The reason the TRAPPIST planets are so significant is that they are accessible to observations with the James Webb Space Telescope. You can see an animation of it here. So with the James Webb, we'll be able to study the atmospheres, and we will try to assess the greenhouse gas content, which will help us understand the surface temperature of the planets. Are they indeed the right temperature to support liquid water and life as we know it? In fact, we're even going to use the James Webb to search for gases that don't belong that might be produced by life, such as oxygen, ozone, methane, and a whole host of other gases.